Last class, we saw uh, that the simple resistive displacement sensor, uh, which, as I already told you, is the workhorse in the industry for displacement. One particular problem of a resistive potentiometer type displacement sensor is the friction between the wiper and the resistive element. So this gives wear and tear, and because of that, any resistive potentiometric type displacement sensor you buy from the market, the manufacturer always tells you, okay, my sensor has only certain operational life. So normally 1000 to 10,000 operations. When I say operations, the one operation is one movement up or one movement down. So that's mainly because of the mechanical wear. One way we can remove the wear is not to have the wiper touch the uh, resistive element. So we make the wiper float on the resistive element, then we get what is known as a floating wiper resistive displacement sensor, right? So in the last class, we saw uh, in my handwriting. Now I have prepared these slides, so they give you a little more clarity in terms of both the pictures and the writing. Now you see here, that's a wiper. This is actually from an automobile, a car, which senses the acceleration pedal using a floating wiper displacement sensor. Oh, this is not an acceleration pedal, sorry. This is a brake wear sensor. So you can see as it ages, you can see that the wiper is really gone bad, and the transducer has to be thrown out. You have to put a new one, right? Or at least put a new wiper. Many times we don't simply we throw the old transducer, and so this is the equivalent circuit we have already seen. Um, so the I have already told you that the apart from reduced operational life, you also have a mechanical loading, because to have good contact, you put a spring and press the wiper against the resistive element. So which increases friction, but it gives you a good electrical contact. There will not be any loose connection. But that is detrimental in reducing the operational life, and also you need to have enough mechanical force to move the wiper, right? We have seen this when we operate a potentiometer in the lab. The lab rheostat is nothing but a resistive potentiometric displacement sensor, and you know how tight it is, especially when it has aged, right? So what is the solution? Of course, we saw in the last class, the solution is I don't use a wiper that touches the resistive element. I put a small air gap between the resistive element and the wiper. Uh, the equivalent circuit is shown on the, this is the equivalent circuit shown on the left side, and because of the air gap, we get this coupling capacitor. Coupling capacitor, and that's normally very small. And if I look at the operation, both here and here, I get R1 and R2 varying with respect to X in a push-pull manner. So when I increase, when I move the wiper up, R1 decreases, R2 increases. When I move the wiper down, the reverse happens. R2 decreases and R1 increases. Anyway, uh, we can use it as displacement with bipolar, that is positive displacement is going up, negative displacement is going down, or we can even put x is equal to 0 to x full scale. It's also possible that we have a unipolar displacement sensor, right? So what uh, happens now is we will have to get an output, because we can no longer use the conventional simple battery connected to the resistive displacement sensor, and the output would be proportional to varying voltage, varying DC voltage proportional to the displacement. Now we need to use special signal conditioning circuit. This we saw in the last class. I am just putting it again so that you get kind of insight. The circuit is exactly the same. You can look at the previous lecture. So we have S1, S2, S3, S4, S5 and S6. 6 switches, and there is an op-amp integrator. With the feedback capacitor, it becomes an integrator. There is an op-amp comparator, which compares the voltage between its inverting terminal and non-inverting terminal, and gives an output which controls these three, that is S4, S5, S6 switches. If the comparator output is 1, S6 will connect a clock to this switch, which means whenever the clock goes from 100, this is the clock. So whenever the clock goes 100, this will switch between minus VR ground, minus VR ground. When this is 1, this will be in this position. So ground is applied, which means this switch will go to 0 and it will stay there. This again is given to V clock. So this will also go from ground to 1, ground to 1, ground to 1, ground to 1. Whenever clock goes from high to low, high to low, high to low. Right? That's the operation. And we have seen that the output of VS4, which will be either plus VR or minus VR, is given to an integrator, which is nothing but a low pass filter with very low cutoff frequency compared to the oscillation frequency. Now this is the integrator, which integrates a charge from CC. You will see that later. That's the comparator, and that's a low pass filter, right? And switches. Now when we have this, whenever this switch goes from 1 to 0, this capacitor will charge, and the charging current will come through CF, and when the switches go like this, it will discharge. Again it will charge, discharge, charge, discharge. So we get the output because the current is in this direction. The capacitor gets charged positively, and the integrator output will be. Please remember, at this point of time the comparator output is 1. Only because it is 1, plus VR is connected here, and this is connected to ground, and this is connected to clock. Right? Once this reaches plus VR, this is VR negative, non-inverting. Inverting input goes more than non-inverting input. The comparator will switch state, right? So it goes to negative, okay? And in the negative, the moment it becomes 0, this goes to 0. You can see here, this goes to 0, and this also goes to 0, which means S2 is permanently grounded, right? And S1 is now connected to clock, and it will go 0, 1, 0, 1, 0, 1, and connecting plus VR and minus VR. The same thing happens. Now the charging current is from a positive voltage. So when I put a positive voltage, current goes in the opposite direction. So the capacitor now will get a charge like this, right? So for each clock cycle, we get VR by 2, 1 plus X by X into CC by CF transferred, but now it is transferred in the opposite direction. right? So we again in this position, you see here, this is ground, so the capacitor is short circuited, right? And again when I go back, it charges and I get the charge transferred to CF. So this happens and finally we get a continuous oscillation. This kind of oscillation is called the relaxation oscillator, right? Only thing is in this case we have a switched capacitor relaxation oscillator. We are switching the capacitors CC, right? Uh, and of course in switching capacitor CC, we also bring in the potentiometer voltage uh, at the wiper point into picture. So we, in the last class, I have already derived this. Time period T1 would be, this is the total minus VR to plus VR. So 2 VR, and each step is VR by 2 into 1 minus X by X CC by CF. So that would be the number of steps here. And please remember, each step is CC, right? This is one clock cycle TC. So if I have 25 steps, 25 into TC will give me T1. Similarly, T2 going down. Now the charging discharging happens with the plus VR. So we get 1 plus X by X into CC by CF as a charge transfer. This would be number of clock cycles that constitute the second period T2, right? So now we look at the output. Output is the low pass function, which means it's an integration. So we have 1 by T integral 0 to T. So this would be T1 minus T2 by T1 plus T2 into VR, which happens, we have seen in the last class, VR by capital X into full scale. So I get an output voltage which is directly proportional to the displacement X, and the proportionality constant is the reference voltage VR. So if I use a very stable reference voltage, that would be a constant, and the full scale of the transducer, which anyway the moment I make it is either 10 centimeters or 10.1 centimeter, whatever it is, that would be a constant. Okay, so we get this nice output. In fact, if you are all on campus, we would have done an experiment. I will not concentrate on this slide. Let me. So, in fact, you can rig it up in our lab and see to it that you get a very nice displacement to analog output. So, this is what we learned in the last class. Now, if this is the actual transducer we will use in the lab. When you come to IIT Madras, we will see when that happens, whenever that happens. Now, the next is we have one signal conditioning. So I told you there are several other signal conditioning circuits. I'll give you the references. You can go through them. But the relaxation oscillator circuit that I've shown is the simplest and the best in terms of simplicity as well as linearity. Now next what we are going to do is a dual slope displacement to digital converter, right? Directly getting a digital output. What this means? So this type of transducers is called direct digital converters, or simply called DDC, right? What does direct digital mean? Now we saw that I have the sensor. This is the floating wiper resistive displacement sensor. This is our relaxation oscillator. And we get an output V naught is equal to VR by X full scale into small x. Right? That's an analog output which is proportional to the displacement x. I keep saying displacement x, but this is equally applicable to an angular displacement transducer theta. There is nothing great about it. The same circuit will work for rotational or angular resistive potentiometric type displacement sensor, which is normal potentiometer with a shaft that rotates. Okay, so the relaxation oscillator circuit gives an analog output. Now, if I want a digital, what I have to do is I take the analog output and put it into an analog to digital converter. I will get a digital output, right? Whatever number of bits I want or whatever number of digits I want, I will get the output as, right? Okay, I think I have not done it correctly. That's nice. So I get a digital output. But is it possible to get a direct digital output from the sensor? We don't use ADC. We simply use a sensor and a signal conditioning circuit, and that gives me the direct digital output from the sensor, right? So this is available for many sensors now. So what we are going to do is such kind of signal conditioning circuit which gives me a digital output directly operating on a sensor, right? Which we call it as direct digital output sensor, or simply called direct digital converter, right? In this case, it's direct digital resistance to digital converter, direct resistance to digital converter. Now, the first thing that we are going to see is the dual slope converter, right? The dual slope principle, as the name indicates, there is a first integration, one slope, right? So this is slope 1, and we integrate again. Many books call it as deintegrate. Of course, they don't call it as disintegrate. There is nothing called deintegrate. We integrate with a negative sign. So again, we have slope 2. So at the end of second slope, in a dual slope analog to digital converter, T2 will be proportional to the input, right? In a conventional sense, we may not have this. We may give an input voltage, right? All your digital multimeters use the dual slope analog to digital converter, and they are very, very popular, right? So in our case, what we are going to do is we keep the structure of the dual slope. So we have a control and logic unit which also houses a counter, and 1, 2, 3 switches, right? As usual, the terminals P1 and P2 of the potentiometric floating wiper potentiometric displacement sensor is connected to single pole double throw switches. So one end of switch 1 is connected to ground, another pole is connected to plus VR. Similarly, one end of S2 is connected to ground, the other end is again connected to plus VR. The output of the right, this is normally we call it as O. The third terminal, the floating wiper, is again connected to a switch which either connects the output to the non-inverting input of the integrator or to ground, right? Now, if I have to ensure dual slope conversion, please remember that I have to start at 0. So I have to uh, ensure that the integrator output is 0, then only I can do the slope 1. So this ensuring 0 at the start is simply called auto 0. All dual slope digital converters will have to have an auto 0 phase, where before starting a conversion you ensure that the integrator output VOI is 0, right? So this is VOI, right? How do we do that? This is the logic for the auto 0 phase, where we look at the comparator output, right? If the VOI is positive, comparator will be 1. If VOI is negative, VOI positive, comparator will be 1. VOI negative, comparator will be 0. Right? So you sense that. If it is 0, which means VOI is negative, you put the switches in this position. If you look at it, the S1 is put to 0, which is connected to VR, and S2 is connected to 1, which means it is connected to ground, and S3 is put to 0. So in this case, the VR charges, and it will charge to whatever positive voltage that capacitor CC can acquire. In the next phase, we shift the S1 and S2. S1 becomes 1, S2 becomes 0, S3 becomes 1, right? Everything is flipped. Now what happens is, please remember, this is at ground potential. This is also at ground potential. So one end of CC is at ground, another end is at virtual ground. So CC will discharge, and please remember it was charged like this. So it was charged with plus minus here. So the current will flow like this. So my output would increase. So here, let's say if to start with, it's some negative output, it will start. Let me put it nicely. So every time I do this, right, I ensure that I do it till VC becomes 0. Please remember, when uh, we started VC equal to 0, we know that the output of the integrator is negative. So we went through and saw to it that the output made. Now on the other hand, if the output of the integrator was 1, which means that the VOA is positive, the switches are now connected as S1 0, S2 equal to S3 equal to 1. I have shown here. So if I look at it, this is connected to plus VR, this is connected to plus VR. So this will be, at this point there will be plus VR, and this is at virtual ground. So capacitor CC will be charged to plus VR, and the charging current will flow here. The capacitor will get a charge in the opposite direction. Please remember, VOA is positive. Now I am sending a charge through capacitor in the opposite direction. That would cancel. This again we do umpteen number of times. Still I get 0, right? Once I get 0, it returns and goes to a logic called the conversion phase. In the conversion phase, we put S1 equal to S2 equal to S3 equal to 0, right? So this is ground, this is at VR, and this is ground. So capacitor gets charged to whatever plus voltage here, right? Plus minus. Now in the next half of the clock cycle, we reverse. Here it is ground. So I have ground here, I have ground here. So the capacitor, this is again virtual ground. Please remember this. So the capacitor gets discharged, and the current now in this direction. So the capacitor gets charged plus here, minus here. That is what I have shown here. So every time we do this, the capacitor gets a charge accumulated from Cc. So each step you can see x VR into Cc by C1. Okay. So this keeps happening till T1. This is a preset period. You can choose 10 millisecond, 100 millisecond, 1 second, whatever it is. T1 is fixed. It's always done for a fixed amount of time. Once T1 is over, at the end, we put the switches like this. Now I see that the capacitor charge would discharge Cy. Already the integrator capacitor has charged to some voltage. Now the charge is in the opposite direction. So this would discharge, right? It will charge plus minus here. Please remember earlier it was plus minus in the opposite direction. So we have the successive steps would discharge, and the discharge step size would be VRCC by Ci. Here it is XVRCC by Ci in the T1 period. And we discharge it till the integrated output becomes 0. At that point, we stop the operation and we find out what is the value of T2. Please remember, this is a state machine. We use a counter and we count in terms of Tc. So T1 is N1 times Tc. For example, I can make N1 to be 1000. 1000 clock cycles will make T1. Now for T2, I discharge using VR, but count how many counts is required to discharge the capacitor Ci, right? So I call this as N naught. So the N naught, oh, there is a problem here. This has to be N naught. N naught can be easily derived. Because the number of cycles on N1 is XVR into N1, number of cycles in XV2 is XVR into N2, that's a charge, and N0 would be X by capital X into N1. So N1 is, as I said, we already fix it, 1000 or 2000, whatever we want, we can fix it. So the second count, the count during the second slope, the count during the second integration period, the count during the de-integration period, as the many books claim, will directly indicate displacement, right? So here again, if I look at it, here the Cc gets cancelled. Cc appears on both sides of the equation, so it gets cancelled. So whatever be the value of Cc and Ci, the output would be proportional only to small x by capital X into N1. Okay, so this again, the output is independent of the coupling capacitor, which is normally a problem when you use a floating Viper. So we can get a direct digital output using the dual slope principle, right? And get a digital number that directly indicates the input displacement X. Once again, I keep saying X. It is also possible that we do the same thing. Instead of linear displacement transducer, we put an angular displacement resistive potentiometer floating Viper transducer. We get output proportional to theta, right? So I can now make a simple direct digital converter for the floating Viper resistive displacement sensor. Now this is quite nice. There's only one problem with the floating Viper resistive displacement uh, direct digital converter is that the conversion time is quite large. For example, I have to integrate first to T1 seconds, and I'll have to wait till T2 seconds to get the output. So typically you get a few conversions per second uh, to few hundred conversions per second. That's the best you can do with the dual slope analog to digital conversion technique. Of course, conversion time is not the strong point of dual slope principle. The dual slope has, as I said, in terms of sensitivity, in terms of resolution, and in terms of noise immunity, outperforms most digital conversion principles. So that way, this is fine. But if you want a higher sampling rate, you want the digital output, let's say a few kilo samples per second, then the dual slope direct digital converter is absolutely useless. Uh, what is the alternative? The alternative is sigma delta analog to digital converter, right? So if we can use a sigma delta analog to digital converter, right, and convert the resistance change directly into a digital output without converting the resistance change into voltage and then convert the voltage to digital converter, we get a direct displacement to digital converter of the sigma delta type. Now let us look at what is sigma delta ADC. I have given the block diagram here. Uh, we have a summer. In the summer, we give the input voltage and compare it with the output voltage of what is known as the 1-bit DAC, and the difference is integrated using an integrator. An integrator output is converted to digital 1 or 0 by using a comparator, and that 1 or 0 is clocked using a clock, and the output of the comparator with a one sample delay is fed back uh, using the 1-bit DAC, and it also goes to a digital low pass filter, right? So let's look at how does it work. So if my input is 0, right, it will connect to plus VR. I will get output rising up, sorry, minus VR, output will rise up. Uh, then this will change to state, it will become 0. When it becomes 0, the output will start reducing. Again, when it comes to the next clock cycle, the output will be latched, and so I will get 0 1 0 1 0 1 0 1. If I take the low pass filter, if I count the number of ones minus number of zeros, this will be 0. I will get equal ones and zeros. Now if I have a voltage which is slightly positive, right, I have taken the voltage to be half the full scale voltage plus VR by 2, we will see that the number of times it goes to 1 would reduce. Number of times the comparator output is on 0 will increase. Okay. Once again, if I look at the number of ones and number of zeros, which actually what the digital low pass filter does, uh, the output, I can get a digital output which is simply representing my input voltage. Of course, what we do is we use the same structure, but we don't use that to convert the voltage to digital. Instead, we convert the displacement to digital. This is displacement X to digital, right? So the scheme is the same. Let me just show you. So if I look at, this is our new circuit, this is the old circuit. You see, this portion is common between the two. I have added only the additional, right? So here again, what happens is, if my integrator output is 0, VC will be high, and that would be latched, and that latch will operate the switches like this, right? So Y is high, 1, so VCL is also high. So these are the conditions of the switches. So what happens now? The current flows through the capacitor, and the capacitor gets charged. Okay, it keeps raising up till it reaches 0, because please remember here the comparator OC, one input is 0, so it functions as a zero crossing detector. If my non-inverting input is grounded, if inverting input is positive, the comparator output will go to 0. If the inverting input is negative, the comparator output will become positive. So it simply checks whether there is a zero crossing has occurred, right? If zero crossing occurs from negative to positive, it will go to 0 to 1. If it is positive to negative, it will go to 1 to 0. That's the only difference. Okay. So during this period, each step will go through it. This is again the same way. This voltage is VR into R2 by R1 plus R2. So multiplied by CF, CC will be the charge that will be transferred to CF, and that voltage will be the charge divided by CF, right? So the output of the integrator will go, it will be 1 till then. Now the moment it goes to VOI, immediately the switches will turn around, this current will now discharge, right? And once again the charge occurs, it will discharge, charge occurs, discharge. So I will get ones and zeros. So here if I take these two, the 1010 clock will be there. Here when the output is 0, it will be 0000, right? So the number of clock cycles for whenever VOI is positive, and hence the output of the comparator is 1, is given by the equation VR into R2 by R1 plus R2 into CC by CF. The number of times VOI becomes 0 is given by the expression minus VR. Now the numerator will become R1, not instead of R2, divided by R1 plus R2 into CC minus CF. So the digital low pass filter now takes the average of this. So if I take the Y average, that is the output, this is the Y, I keep one like this, that becomes X by capital X. So I get a number which is proportional to the displacement. One good thing here is you see that VR also doesn't come into the picture, because VR charges and VR discharges. For both charging and discharging, we use the same VR. So VR gets eliminated, and the output is directly proportional to the displacement X. The proportionality constant is 1 by capital X, where capital X is the full scale voltage. Now again, you can do what all will be the errors. I am not going through this slide. If you are interested, as I said, I have uploaded the notes and everything onto the Moodle, okay, and you can peruse the material there and find out what it means, what are all the errors that can happen in this type of conversion, and more importantly, how to choose the components. For example, you choose an op-amp whose offset voltage is very small compared to the reference voltage VR that you have chosen, right? And again, charge transfer, switch resistance should be low enough so that the it doesn't create error in the output. There is another problem with switch called charge injection. So you must use all the 1, 2, 3 switches must be of zero charge injection type switch, which is available. It's a particular configuration, device configuration, that gives zero charge, right? Again, this is missing. If we have been in the institute, we would have done this simulation on circuit simulation called LT Spice. Those of you who are interested, you can go to the websites of semiconductor device manufacturers. For example, there is a semiconductor device manufacturer called Linear Technology, right? They have a SPICE simulation software which is free. You can download the full version and simulate any circuit and see. So that is called LT Spice. The other company called Texas Instruments, they also have a similar circuit simulation software. So all the signal conditioning circuits that we have discussed, you can simulate on the software and see that it works nicely and it works as. Uh, One of the advantages of sigma delta principle is called the noise shaping, right? So what happens is the inherent filter, the low pass filter that you have in the digital side and the integrator that you have on the input side, both are noise cancelling circuits. So you get what is known as the noise shaping circuit. So you get a signal to noise ratio of about 66 dB if you don't take any effort. But if you take an effort, you can also reduce the number of the amount of noise in the output, right? Uh, so again, this is the prototype that we would have used this in the lab. Um, so I stop here. We have one more signal conditioning circuit that is suitable for floating wiper resistive displacement sensor. Um, we will see that in the next class, right? So, see you.